In the textbook, we've derived an eigenvalue equation for the magnetic field. Question is, can you now do something similar for the electric field? So pause the video to do exactly that. Starting point is obviously Maxwell's curl equations. So let's write these down. So on one hand, we have that the curl of the magnetic field is J omega epsilon E. And we also have that the curl of the electric field is minus J omega mu H. Now what we should do is come up with a single equation for the electric field. So obviously the plan is to calculate the value of the magnetic field from the second equation and then substitute that in the first equation. So if we do that, for the first equation becomes the curl of the magnetic field, but from the second equation we know that the magnetic field is 1 over minus J omega mu, curl of the electric field, J omega epsilon E. Now what we have here, so 1 over J omega mu, this is a constant, provided we're working in non-magnetic media. So we can safely bring this outside of the differential operator and also move that to the right-hand side. So we can clean this up a little bit to have that the curl of the electric field is omega squared mu epsilon E. That's a nice equation, and at this point in time it becomes very tempting to assume that curl here is going to be our operator for the eigenvalue problem of the electric field, and that this thing over here would be our eigenvalue. Tempting as this may be, it's unfortunately very wrong, because let's not forget, in our situation here, epsilon is not a constant, rather it's something that can vary as a function of position. So it's not a constant, and therefore it cannot be involved in an eigenvalue. Actually, what we have here is not a normal eigenvalue problem, but rather a generalized eigenvalue problem, where we have a second operator here that first operates on the electric field before you have the actual eigenvalue omega squared mu. So in order to turn this from this generalized eigenvalue problem into a normal vanilla eigenvalue problem, we basically need to move this epsilon here to the left-hand side. And that we can do as follows. So then we have 1 over epsilon curl of the electric field equal to omega squared mu E. Omega squared mu this time is a very constant, so this can serve as our eigenvalue. And then here 1 over epsilon curl, that's going to be the operator for this eigenvalue problem. So that's half of the work done. The next half here is about trying to figure out whether this operator is Hermitian or not. So take a couple of minutes to try and figure this out. So what do we need to do in that case? We need to look at a scalar product where our operator first operates on either the first or the second factor and see if those are equivalent. So let's write down the following scalar products where we first have f and then we have our operator 1 over epsilon curl as follows. And the question is this equal to the situation where this 1 over epsilon curl is first operating upon f? Now I'm going to stick to this notation here, but you should bear in mind that what's behind this here is basically an integral, a volume integral, where the first factor, f in this case, is under a complex conjugate. So that's important to bear in mind. Now what we will be doing is we will be trying to reassemble this operator here, moving it from the second factor to the first factor. And the first layer of the onion, the outer layer of the onion that we're going to tackle, is this 1 over epsilon. We're going to pry that away from the second factor and try to move that to the first factor. Now the question is, can we do that? We should not forget the fact that this f here is under a complex conjugate sign. So provided that epsilon is a real number, we can indeed write down the following. This becomes 1 over epsilon f, and then we have curl of G. So only for lossless materials can we do this, but that way we have sort of like started breaking this operator apart and moving it to the first factor. The second layer of the onion is the curl. Now, there is a formula in the textbook that allows us to do exactly that, to bring a curl from one factor to another factor, where we consider here 1 over epsilon f as a new single vector function. So we can indeed write down that this is equal to a curl that we brought over from the second factor, 1 over epsilon f, and then we have another curl that's still left over in the second factor. But there is a small price we pay for doing that, and that is some stuff involving what happens at the boundaries. Now, as usual, we're going to make the assumption that at the boundaries this term will vanish, will become 0, because either fields vanish at infinity or they're periodic, and if you integrate them out, then they will also have a 0 net result. So we're going to neglect, or rather assume, that this second term is 0. And then moving on, the final inner layer of the onion is this remaining curl, which we will bring back to the first factor in a very similar manner. So then we have curl 1 over epsilon f g plus another factor, which is 0. And the question is, are we now able to say whether this is a Hermitian operator or not? Well, we can conclude that this is not a Hermitian operator, because what we would rather have is that we had 1 over epsilon curl rather than having curl 1 over epsilon. And these two are very different, especially, of course, if epsilon is a function of r, because if epsilon depends on the place, then if you take the partial derivatives with respect to the spatial coordinates, then things will change, which you not do here, of course, because there it's on the outer side. So, conclusion, these two are not the same, and therefore the operator for the eigenvalue problem of the electric field is not Hermitian. Pity, but that's life.